Welcome, Physics 264 students, to your 10 minutes of bliss for this week. I'm Dr. Steve Brule, and today's lesson is on the Wheatstone bridge problem as an illustration of Kirchhoff's laws. As you'll recall from lab last week, we had a Wheatstone bridge where we were trying to measure the resistance of this combination of resistors. These are the values up here, and we were able to put an ohm meter in to measure that in multisim, but we couldn't calculate it using our normal methods because none of these resistors are either in simple series or simple parallel. So the technique that we will apply today is we will apply a battery to this circuit and then calculate how much current is drawn from the battery by this circuit. And then once we have how much current is drawn from the battery, and we already know what the voltage on the battery is, we just take the voltage divided by the divided by the current, and we have the equivalent resistance of that combination of resistors. Now, the way we will calculate the current going into this Wheatstone bridge, this source current right here, is using Kirchhoff's laws. You'll notice that we have 6 unknowns. We've got the unknown that we want. This is the only one we really need, but then that breaks off into 2 currents here, a current through R1, current through R4. There's a current through R3. I'm putting it in as down. You could easily put it in as up, and then if you guess wrong, then when you solve the simultaneous equations, you'll just get a negative sign, which will indicate to you that your direction that you guessed is actually the other way. So here's a current, and then there's a source current coming out again. Okay, well, let's start by writing some equations for each junction, because the junction rule is the easiest of Kirchhoff's rules, so we always start with that one. Let's start with this junction right here, and whenever there's a current coming into a junction, we call that a positive current. When there's a current coming out of a junction, like I4 and I1 are both coming out of that junction, both of them are negative. So we've got plus IS minus I1 minus I4 equals 0, and that's our first equation. So we're going to need 6 equations to solve for these 6 unknowns. Here's another junction right here. We've got I1 going in, so that's positive. I3 is coming out and I2 is coming out. So both of those are negative, and that's equal to 0. So the sum of currents in to a junction is equal to the sum of the currents out, or the net current at a junction is going to be 0, and that's how we get our equation. So that's equation 2. Let's jump over here to this node right here. We've got I3 coming in, so that's positive. I4 is also coming in, so that's positive also, but I5 is coming out of that junction, so that's negative. So we've got I3 plus I4 minus I5 is equal to 0, and that's yet another junction equation. And for our fourth junction, we had 4 junctions in this circuit. This 1, 2, 3, 4. Junction is any place where 2 or more wires come together. And at this one, we've got I2 and I5 coming in, so they're both positive, and IS is going out, so that's negative. So it looks like we've got 4 equations out of the 6 that we need. But we have a problem, and I'll show it to you right now. First of all, let's just solve for I1 in this equation to illustrate what the problem is. So I1 is going to equal I2 plus I3. This rewriting equation 2. Rewriting equation 3, we end up with I4. I'm solving for I4 because I'm going to plug them back into equation 1. So I4 is equal to I5 minus I3. So I just move that to this side, subtract that from this side, and I get this equation. So now I jump down here from equation 1 and substitute in for I1 right here and I4 right here that I calculated here. Do a little bit of math, and I end up with this equation. And here we found is the same equation as equation 4. So by solving these three equations simultaneously, we got this equation. And that's what you have with the junction rules, that if you have 4 junctions, you'll have 3 independent equations. And that's how it works. If you have 8 junctions, you'll have 7 independent equations that you can write from those junctions. So there we are. We have 3 independent equations. That was our n-1 junction equations. So now we need to write 3 Kirchhoff's loop equations to get the rest of our equations that we need to solve for our 6 unknowns. Well, I just arbitrarily picked this as our first loop going along like that. So any loop in the circuit that you can draw is a valid Kirchhoff's law rule loop. So here I have plus, as I go along I'll show you how I do these. People have their own ways that they like to do it. But when you go over a battery, so I'm starting my loop right here, I'm going through the battery from a negative to a positive, so that's plus Vs. And whenever I go, I'm going right here through a resistor, if I'm going in the same direction as the current, I drop voltage. So that's minus V equals IR, but I'm writing it as RI because I is our unknown, so I wanted the constant in front of the I. So I'm subtracting the voltage because I'm going with the current. Then I'm going with the current again right here in R5, so that's a minus R5 times I5. Come around here and I get to where I started, and then we equal to 0. So the idea with Kirchhoff's loop rule is you go around a loop and the sum of the voltages around any loop is 0. Let's do another Kirchhoff's loop equation. So that was our equation 4. Equation 5, I went around the outer loop here. So we start right here. We get plus Vs minus R1 I1, so that's this term right here, minus R2 I2, because again I'm with the current, and I get back to where I started, and we've got our 5th equation. Then we go to, I just arbitrarily picked this loop. It says 2 arrows there. It should only have 1. Okay, so we're going to go, I start at the top, so let's get this right. So I'm starting here, going through R1, so that's minus R1 I1. I'm going with the current through R3, so it's minus R3 I3. But now to come back here, I'm going against the current in R4, and if you're going against the current, that means you're increasing voltage. So that's why I said it was plus R4 I4. And then the sum of the voltages around that loop are 0. And we could write, so now we have our 6 equations. We could write other loop equations. We could write this loop. We'd have another equation. We could go through this loop. We'd have another equation. We could do, did I say this one? That's a new loop. So any one of those loops is fine to do. Okay. But we only needed 6 equations, so we stopped there. I rewrote equations 4 and 5 just to show you what they were over here. I'm just plugging or moving the source voltage to the other side. I subtracted from both sides and multiplied everything by -1 to get a nice equation there. And the reason why I'm doing that is because I'm setting up these. We have these 6 equations, and I'm going to set them up so that Matlab can solve the equations simultaneously. So we don't have to do it the way we did it in 7th grade when we had simultaneous equations. We're going to just feed this into Matlab, and it's going to solve the equations for us. Well, before we can feed it into Matlab, we have to give Matlab the equations in a way that it can understand them. So, for example, equation 1 I write as, and I'm always going to write IS, I1, I2, I3, I4, I5, and then it's equal to some voltage, which would be, or whatever is on the other side, which in this case is going to be 0. So I have 1 IS minus 1 times I1. I have no I2s, no I3s. I have minus 1 I4s and none of the I5s. And that's all equal to 0. So that's how I wrote equation 1. I could write equation 4. Here was equation 4 from the other page. And I have, now we're multiplying r's times i's, and then they're going to equal v's. So I have 0 of the is's, 0 of the I1s, 0 of the I2s, 0 of I3s, because none of these terms appear in equation 4. But then here we have 4 of the I4s because IR4 was 4. And then for I5 was 3 ohms, so I've got 3 I5s. And then Vs is equal to 10, the source voltage that we arbitrarily chose. Well, you could do that yourself for these other equations that we didn't work through together, but these are the 6 equations now written in terms of every one of the unknowns that we are trying to solve for. Okay, now we make this into a matrix so that this is 1, negative 1, 0, 1, negative 1, 0, 0, negative 1, 0, 0, negative 1, 0. So that is equation 1, just the coefficients in front of the variables in that main matrix. Then this set of coefficients goes down here, 0, 1, negative 1. See how this is working? Then negative 1, 0, 0. And so on. So I just took all of those coefficients and moved them into a nice matrix for Matlab. And now Matlab, which uses matrix algebra, will take this matrix. We're going to tell Matlab what the matrix equation is. Well, I do it in the next one. So this is the resistance equation. These were all the resistances in front of the currents. This is the, I should have said matrix. That's a resistance matrix. Here's the current matrix, and that's equal to the voltage matrix. So Ohm's law would be R times I equals V. And normally, if we wanted to solve for I, we'd just say I equals V over R. But here's the twist. Matlab uses this thing called left divide, so instead of writing V over R, it writes V over R backwards. And when you do that, you're telling Matlab to solve these equations simultaneously for you and return a matrix of I that solves for that matrix of unknowns. Well, here is the Matlab code that does that. It's very short. There's the matrix that I just plugged into Matlab. Here are the voltages that I knew. So it was mostly zeros except for those two equations. It had 10. And then here is that left divide term. I hit return, I run that thing, and it gave me all of the currents instantly. This was IS, this was I1, 2, 3, 4, and 5, but this is the only one that we need. Because remember, we just needed to know the total current coming out of that battery so that we calculate the equivalent resistance. So now that we have the total current, I just take the source voltage that we applied across our Wheatstone bridge, divide by the current that Matlab found for us, and I get this is my total resistance for the circuit, or the equivalent resistance. I ran the same thing in multi-sim by putting the resistors in like we did last week in lab, turned it on, and look at that. It's the same exact resistance. Well, this will conclude your 10 minutes of bliss for this week. I'll see you in lab.